Hey, Nathan here, welcome back to another video game algorithms video. In this video we are going to discuss obstacle avoidance artificial intelligence. Last video we discussed wandering artificial intelligence, where we have a game object in our world and then we apply the wandering artificial intelligence logic, and that object can now freely wander around the environment. Now, one thing you want to include with the wandering artificial intelligence is obstacle avoidance. We don't want to have that object run into bad enemies or bad obstacles. So that brings us to obstacle avoidance, where we want our game object here to avoid obstacles here. So our game object does have a velocity. It is using wandering artificial intelligence. So let's say our object's velocity is this. So that's our velocity. Now, we want to avoid these three boxes. In order to do that, we need to calculate a safe distance away from the box. So each one of these boxes will have a barrier around them, a distance threshold, and if our object is within that distance threshold, we need to implement obstacle avoidance. Alright, so our object is this here. It's going to be very large. We are zooming in, so where we can closely see what is going on. And let's make our box this orange color. So our box is going to be here, very close to our object. Okay, so in order to calculate if it's within our threshold, our distance threshold, remember there's going to be a distance threshold from our object. It'll look something like this. But if our player is within that distance threshold, we need to implement obstacle avoidance. And we are using the center point of our game object as our position. So right now we can see this object is within our distance threshold. So we need to calculate. Let's put a center point here as well. Alright, so we need to calculate a distance vector. We're going to call this target, and we're going to call this source. So the distance vector is going to be our target.position minus source.position. So that will give us our distance vector, which will look something like this. So this is our distance vector. It has a angle as well. So our distance vector is this. Now we need to know for sure if our object is within our distance threshold. What we need to do here is we need to calculate a length. And that's going to equal the length of our distance vector. So the length of our distance vector, that's this part here. That's the diagonal. So if length, let's put code in blue. Okay. If length is less than some threshold, if length is less than some threshold value, then we need to perform obstacle avoidance. So that means we need to calculate an adjustment vector. So an adjustment vector is equal to our distance vector. We already calculated that, but we're going to be manipulating our adjustment vector. Next, we need to calculate the difference between the length of the distance vector and our threshold value. Because the closer we get to our object, the closer this player gets to this object, the more intense we want it to push back, the more intense we want the avoidance to be. If it's barely close enough, if the object is moving this way, then we barely want to adjust its positioning here. But if it's pointing this way, going very fast, we want to make this a much harder push away from the object. So we want it to essentially be like that. So we need to calculate the difference between our threshold and our length. So let's put this in here as well, in this color as well. So our difference is equal to our threshold minus our length. Minus the length. So our difference is our threshold minus our length. So that will give us a more intensity. The closer we get to the object, the more intense our object is going to be pushed away. Then we need to normalize our adjustment vector. Normalize adjustment. And then we set the adjustment is equal to adjustment times the difference here. So the bigger the difference, as in the smaller this vector is, the bigger the difference is going to be, which is going to be a more intense push in the opposite direction. Now, this is source. So we have a source.velocity. Now, it's potentially moving, it might not be moving, but we assume that it has a velocity, and then we set that as equal to the velocity minus the adjustment vector. So the velocity is now the velocity subtracted with the adjustment vector. And then we need to do the same thing. We need to normalize. We need to normalize s.velocity now. And then we need to multiply it by its speed. Times s.speed. So this is what we do. So our object is here. Our box or the obstacle we want to avoid is here. The distance is here. So if the smaller this is, the more intense the desire to avoid the object. So let's say our object's velocity, in this example, our object's velocity is this. It's pretty small. Our adjustment vector here is the opposite, but it's going to be very strong. So that's going to be our adjustment. So V minus adjustment, and let's put minus in green here. No, let's put that in red here. Let's put that in red too. Alright, let's set that as equal to NV for new velocity. So our new velocity is going to essentially look something like this. So as our object gets closer and closer and closer to our box, it's going to move downwards. And if it gets very close, the more intense the push is going to be. So it's going to do something like that. Assuming our velocity is this. So our velocity is going to be adjusted to where it's going to move downwards. But it's going to do that by combining the velocity here. Because we still want it to move in that direction, but we want to avoid that obstacle. So we'll go down here. So the smaller the distance is, the more intense the desire to avoid the object. If it's right next to the object, this is going to be very large. If it's barely within the threshold, it might look something like this. So the closer you are to the object you want to avoid, the more intense the desire to avoid it, which means the more intense the vector is to adjust by. So this is obstacle avoidance. It's a very simple concept where you calculate a distance vector between the source, which is here, and the target, which is here. So we calculate the distance vector, which is here. Then we get the length of that vector, which is the diagonal, the length of the vector. And if that is less than the threshold, we need to perform obstacle avoidance. Obviously, if the object is here, or if our player is here, and the object we want to avoid is here, we do not need to do obstacle avoidance. And let's say our threshold is like this, for example. There's no need to do obstacle avoidance. No need to do avoidance. So no need to do avoidance here. Because that our source is very far away from our target. No need to do avoidance. So if our length is less than the threshold, our threshold is this imaginary circle around the object. So if it's less than our threshold, we need to perform obstacle avoidance. In order to do that, we get the adjustment vector, which is the distance vector. And by the way, our distance vector points that way. If our source is here and our target is here, our adjustment vector points this way. We want to push the object away from the target. So our adjustment vector is our distance vector, and then we get the difference between the threshold and the length. We do that in order to calculate the intensity we need to push back by. The smaller this is, the more intense we need to avoid the object. The smaller the length of our distance vector means the closer we are to our object, which means we need to push back very hard to avoid the object. Then we normalize the adjustment vector, we multiply it by the difference, and then we update our velocity by having the adjustment vector subtract by our velocity's value. Then we normalize that and multiply it by the speed that our object actually travels by. So this is obstacle avoidance. It's a good idea to throw this on top of wandering. That way a wandering object doesn't run into bombs or walls or things like that. A variation of this is wall avoidance. It's very simple. It's a similar concept. Very simple, but you use the entire sides of the window to avoid. Imagine those as 1 pixel by whatever size the window resolution is you use. So wall avoidance is a variation of this, and it's almost exactly the logic that you see here. Alright, so that's it for this video. I hope you enjoyed it. Next video is... Let me bring up the calendar. Next video is going to be a fun one. Getting finished with all these simple concepts. Next one is going to be very fun, hiding AI. That's going to be used to determine when an object is looking at you and you have some kind of box or barrier next to you, how you can position yourself in between a opponent and yourself to where the obstacle is blocking the way. So that way the enemy does not see you anymore, they just see the obstacle. Alright, so I hope to see you next time.